Now, Kristen McIntyre's call sign is K6WX. And now Kristen at the moment is, I think, the VP of ARRL. Is that
That's
correct,
correct.
Kristen?
Yeah,
Yeah.
first VP.
And is on the west coast of the US, so coming
Hmm.
to us from that time zone this morning. So her innovative presentation gets us thinking about our understanding of grounding. So across to Kristen, over to you.
What I'm going to talk to you about today is ground is a myth. And I'm going to present the case that there is no such thing as ground. And we'll see if you agree with me at the end. So what's a ground? And I know maybe there you call it earth, we call it ground here. It's the same concept and maybe the same, maybe muddled concept. So have you ever wondered what this thing is? I think a lot of ham radio operators just kind of accept it as something that's meaningful, but I'm not convinced that it really has any meaningful definition. You know, we've seen it on schematics with all these symbols, but what does that really mean? Well, maybe it's about a reference point. Could be, zero reference to something in a circuit, often refers to voltage. It could be an energy state. We've heard about ground states and excited electrons. That could be it. Can be common connections that may not be any particular voltage, just a wire wired together. And it has this implication in the name itself of some sort of stability, unless you live in California, where the ground is not really stable. Or perhaps it's something about the earth, objects in contact with the earth, objects dug into the dirt, could be about the charge state of the earth, or even the distance from the center of mass of the earth, something like that. And I want to talk about gravitational potential energy in this context because it has a lot of similarities. So gravitational potential energy is, we define it in physics by mgh, and that's the mass times the gravitational acceleration times the height. But what's that height? Is it the height over from a chair to the floor? Is it the height from the center of mass to the Earth to the top of some mountain? Is it something else? Well, it's maybe all of those things at once. But what if there's no Earth? We still have a definition for potential energy, and Newton's law of gravitation still applies. So we can calculate those forces and calculate the potential energy that might be generated by two masses just out in space, because they're going to pull on each other with the standard gm1 m2 over r squared. And this is just like the voltage in an electric field. So let's look at it in terms of voltage. So this diagram is meant to give you an idea of two charges in a field, and I've drawn the equipotential lines, which are circular in this case. We're just taking a two-dimensional model here. And it marks voltage marks your positions relative to these two particles. And it says something here about how much work can be done. And work has a very specific definition in physics. It's a force times distance is one definition. And potential energy is how much of that force time distance you might be able to extract from the system. And this system has a conservative field, which means it's path independent. Not all fields are conservative, but voltage is, the electric field is, as is gravity. So there's no path dependence. So with that in mind, is there a ground for voltage? So voltage defines the difference of position in this electric field across this electric field gradient. The particles could be, both plus or both minus. In one case, the force is pushing out. In the other case, the force is pulling in. But where is the zero here? There's no reference point. Maybe it's somewhere at the edge of the universe. If you get out there and you find it, let me know. Although I may not be able to receive that message for an infinite amount of time. But there's no zero that I can find here. There's just 2 points and measuring between them. Now, circuits have a notion of ground that we've assigned to them. And in this case of the schematic at the top here, you can see it's a common reference point. All these things are effectively tied together in this amplifier at the top. It might mean that we tie that to the chassis of some box or a radio or something like that, and that box might be used to shield the circuits inside, or we might have a shield that goes on a piece of wire, and we might call that ground or connect it to ground. And what happens though, if we have like at the bottom picture on the left, if we have one side with one ground and the other side with another ground, and we hook that shield to one side but not the other side, what does that mean? And in some cases, like in automobiles, it's often a current return path. And so we take the car chassis and we use that like a big wire. And you can see there's a whole bunch of different symbols there. And what do those mean? They're all a little bit different. One says earth ground, power ground, signal ground, additional grounds. I'm not sure what that means. Are they the same or are they different? And then when we start designing with digital and analog, we often have a digital ground and an analog ground. So we split the system up and we put analog ground on one side and digital ground on the other. And that's because, you know, with digital circuits, we often have these high rise times, very fast rise times that give rise to high current spikes. And we don't want those current spikes affecting our analog ground. But what does that mean? So we're going to examine that in a little more detail in a moment. But we have these two separate systems of ground, and how do we join these things back together? Well, that's an interesting question. Sometimes we tie them together at a certain point, but is that really the optimal thing to do? What if there's kind of a voltage differential between these two things or current flowing between them? And then we loop it back to another point in the system. Then we have a so-called ground loop. And if ground were really a real reference, then that wouldn't be a problem. But sometimes it becomes a problem because ground isn't exactly what we think it is. So let's examine a little schematic, very simplified system. So in the most common case, in circuits at least, we have ground as a return path. And so you can see in this circuit here, we have some voltage and it's like an AC generator, but we can ignore that and say it's a DC generator for this purpose of this discussion. And it goes through, V1 goes through some resistor, R1, and it goes to ground. And then we have another V2, a different voltage reference, and then these two terminals labeled V out. And then we have this dotted line resistor, and that's the ground resistance. So there's kind of a phantom resistor there. And that is true in all systems that are practical. And, you know, you could say it's zero in theoretical circuits, perhaps. But in any practical circuit, we have some ground resistance. And so there's going to be current going from V1 through R1, developing a voltage across that. And so current's going to flow through the bottom. So if we go here and we measure what the voltage is at V out, we'll get a certain value. But that value is dependent on the current. So if we have V1 is larger and we have more current through R1, that V out is going to change. And if that's an AC circuit, for example, then it's going to get really interesting. And what we could ask again is, what's that voltage between that V2 and the actual ground, if there is such a thing? And we might be able to measure this at one point where we can figure out what RG might be, but RG might not be linear and it might not be a resistor. And we can go to another point and it won't be the same. So there's no reference here that I can find. Now, when it gets to AC, things are getting really tricky. So here's a typical three-phase AC circuit, or not circuit, but waveforms. Now, where's the ground here? We've got three phases, 120 degrees apart, changing all the time. And you can kind of draw a line across the zero there in that diagram. But there's no wire that defines that zero. All the things are changing, the voltage and the current changing with time. And the three-phase one is a nice one because we don't get any common zero crossings. But where's zero there? And here's an interesting case to look at. So there's, at least in the US, there are two common configurations for three-phase motors, for example. And that's the delta configuration and the Y configuration. And you can see the Y configuration on the top has some kind of thing called a neutral. And that might be, you know, that zero, that reference we're looking for. Well, it turns out that there's a very relatively simple linear transformation between the Y configuration and the delta configuration. They're electrically and mathematically exactly the same. There's no difference between them, except that in one case you can extract that wire and in the other case you can't. And so if we have a motor that's running in the delta configuration, what happened to that neutral? Well, it doesn't need to be there. That's what we call an overspecified system. And so there's no inherent 0 point, no inherent ground or reference here, because the delta configuration exists. That says that there's no way to ground that. And if we go to something simpler, like split phase, in the US, this is very common in homes. We have a neutral and then two hot legs, they're called. And in the US, that's 110 or 115 volts on each side of opposite phases. And how that works here is that there's a fairly high voltage sometimes that's brought in on from external wires to a telephone pole or something underground. And then there's this transformer, and this transformer is a really cool device. And I have a whole talk about transformers because they are very interesting. But what it does is it magnetically isolates voltage. So you transfer power across the magnetic field between the primary and secondary windings. And that allows you to isolate voltages. And you can isolate them to arbitrarily high values if you have good enough insulators. And so the voltages on the right-hand side actually don't bear any relationship to the voltages on the left-hand side for all practical purposes. And then we take that right-hand side of the transformer, which is center tapped, and we call that neutral. And we stick that into maybe some copper pipe in the ground, or rods that are driven into the ground, or mesh under the ground, or something like that. And we call that neutral. But is that really special? Not really, I think. You know, this thing is decoupled from the power that's coming in. It couples across the magnetic field. The voltages are decoupled. We just declared it to be interesting. We've declared it to be related to the dirt underneath your house, perhaps. But there's nothing inherently special about that. Now, of course, we have various electrical codes. I'm sure you have them there in Australia as well. And here in the US, we call it the NEC, the National Electrical Code. And they have ways that they connect these neutrals and other things in your house to pipes or other things that are stuck into the dirt. And that's all very interesting. And I urge you to follow those wherever applicable. I'm never going to tell you not to do that. But it's interesting to think about what that means. And since we put something into the dirt, does that mean that if we stand, you know, a few feet away from where that goes into the dirt, and then we touch that wire, that will be completely safe? Well, not really, because the ground, the dirt, is generally a pretty poor conductor. It's quite variable, depends on the amount of salt in the soil, the type of soil, the water that's in there. So all you need is a rainstorm and you'll get something really different out of this pretty quickly. Now here's a device that even has ground in the name. In the US, we call these ground fault interrupters. And here we find them in kitchens and bathrooms, other places where water tends to be. And it's kind of an interesting device. Let's see if it has any notion of ground in it. So what there is a toroid. And this toroid is meant to kind of concentrate magnetic fields and couple them. And we have two wires that would be, you know, the neutral and hot leg is what it would be here. It doesn't matter, it's just nomenclature. And we pass them through this toroid. And if those currents are perfectly balanced, then there'll be no net magnetic field in the toroid. And on the toroid itself, we pass a few windings around the outside of that so that we can capture a voltage that's related to any changing magnetic field within that toroid. And then we use that to maybe trip the breaker in there. And so if those two are perfectly balanced, there's no net magnetic field, there's no magnetic flux, thus no voltage. And so we don't trip that breaker and it works fine. But if they're imbalanced, if there is an imbalance in those two conductors, then we do get that magnetic field changing with time. And we do get a voltage that's induced in that little winding, and bang, the thing cuts off. So that's pretty cool. If those things are unbalanced, it implies that there's some current going somewhere, so that we have less magnetic field on one side versus the other. and the current's going someplace that we're a little worried about where it went. We're not sure, and that's a bad thing. And so we trip the breaker, and that's great. But that doesn't necessarily mean ground. It just means current's going somewhere we don't expect. And so it's a useful device. It does something great for safety, but I don't think we found ground there. If we look at the conductivity of soil, it's all over the place. I think we have about how many orders of magnitude here? At least 3 or 4 orders of magnitude variation by moisture, soil type, and salt. Salt makes a huge difference, of course. And so we can go anywhere from 100 ohms to 250,000 ohms, depending upon what's going on with the soil and what has happened with the weather recently. So this is a very interesting thing to know again. But does this imply that putting things in the ground is going to improve safety? Well, it all depends. It's not entirely clear. So the point here is that the Earth is not a very good conductor, or it's certainly not a consistent conductor. But you say, don't antennas need a ground? We always talk about that in that context. Well, if you have a balanced antenna, consider a dipole, there's not anything that favors one side of the dipole over the other. It's a perfectly symmetric structure. And so there's one side is as good as the other. Now we may put the shield of the coax on one side, and that may unbalance it in some way, but that's not anything to do with the actual structure itself. If it's in free space, then that thing is exactly symmetric. So that doesn't find a ground there. And if we do connect the shield of a coax there, what have we done? Well, we've added the shield to the antenna system and thus created a new antenna system that'll have slightly different characteristics around the impedance, the dry point impedance, and the pattern. And that's kind of interesting, but it's just a matter of what wires we have in the air. Sometimes, especially on Yagi, we will have something called a gamma match, which is pictured here. And we might connect the shield of the coax to one side of that. And that's an asymmetric structure in itself, but it doesn't have to be that way. We also have this thing called the delta match, and the delta match is, again, symmetric and achieves the same ends, which tells us that it doesn't have to be that way. It can be other ways, and that we've chosen to unbalance the system and add wires or change the arrangement of wires and change our pattern as a result. So there's nothing here that's inherently ground-like. Now, what about ground planes? Now, a ground plane is an antenna that, well, again, it has ground in the name, so yeah, it must have a ground, right? But they're sort of compact versions of dipoles. They have a reflecting plane, as you can see in the bottom diagram, where it pretends to have a mirror of the top part in non-space. So the way that if you ray trace the signals, you'll see that they kind of do an equivalent thing, but we get just half of the antenna, but we get the same general effect. So I call these monopoles, and as opposed to dipoles, but they're sort of act like dipoles, but they have half the drive point impedance, and they're more compact. And we have these things called radials, and they form in somewhat imperfect version of this mirror on the bottom. And we can have as few as 2 if they're elevated. And they make this antenna possible. But is that really ground? Well, not really. It's just a particular antenna structure that has a reflecting plane. So you don't really have to have them there. You could put the other half of the antenna down at the bottom, and that would work just as well. Now, balance, we have these things that seem to connect to ground. We see the ground symbol there. But what do they really do? Well, they're transformers. And remember from our earlier discussion, that transformers are a great way to decouple voltage from two things, but still transfer power. And so how we connect them together is just our choices. And so we might connect some parts of this transformer to the shield of our radio. We might connect it to one side of the coax. We might have the windings arranged in interesting ways to shift the voltage around one way or the other, or invert it or whatever. But again, these are choices we make. There's nothing inherently ground-like about these. So it's not even an earth ground in many cases. It's just a way of decoupling voltage or recoupling it in a way that we want. And you can see this most clearly when you use the classic transformer, like we talked about earlier, where there's absolutely no voltage coupling whatsoever. And that's very common. We call this voltage balance in many cases. And they're very effective, except for the losses in the core. But that hasn't found us any grounds there. We're often told, don't use the neutral or safety ground as the system ground. And that's probably reasonable advice in some cases, because you might be coupling to things that you don't realize what they might do, or they might put some RF in your house that would cause things like alarms to go off, or smoke sensors and things like that. And so in many cases, we're told to put in a ground rod. And that's a piece of pipe or a piece of good conducting metal that we drive into the earth. But why are we doing this? Let's examine that in a little bit more detail in a moment. But do keep in mind this diagram we have here, where we have the exposed wire on the shield of the coax. That's important. Now, what about power supplies and grounds? Well, this is where I get really confused. So if we have a power supply like this one in the picture, let's say this one actually has 2-wire power mains coming in, but let's say the 3-wire one that has the safety ground, and I have power supplies like that, and you plug that in the wall, so you got the safety ground going on, and then you have plus 12, minus 12. Is minus 12 connected to any of this? And then we have this screw on the back that says ground. What do I do with that thing? I have no idea. And where should I connect it? Not clear at all. Now, with all of this, is your head beginning to spin? Where's the ground? Where is this 0 volts? And then we add in RF, and then it's even more confusing because I move a little bit to one side or the other, and I've changed my position within these oscillating fields, and there's a gradient there, and things have changed again. They're all changing with time. We're inducing voltages and currents in other things around us that are warping those fields even more. And so I really have no idea where 0 volts might be found within this. So what I've decided is this is an impossible thing. There's no ground. Everything is relative, everything's in motion. And the best we can do is differentially stabilize all this stuff so that we don't get hurt and things do what we want them to do. How do we do this? Well, I have 3 principles I want to leave you with at the end of this talk, and they are shield, isolate, and stabilize. And let's take a quick look at those 3. Shielding is Faraday shielding. If you've ever done this calculation, if you took an E&M course, it's pretty straightforward, where you can show that if you have a perfectly conducting enclosure, you will have no electric fields inside that are not from charges that are already inside the box, and certainly no time varying electric fields. And if you have no time varying electric fields, that implies that there are no time varying magnetic fields, and that means no RF. So this allows us to shield something away. And you often see this in RF amplifiers to shield the various parts of the amplifier from each other: power supply from the input filtering, and then the power part, the amplifier part, and its output filtering, so that they don't talk to each other. Isolating, it's really important to isolate different signal paths so that we don't have things that leak between each other, the fields that leak between things. So we want to get rid of common mode currents. So we use ferrites to create a high impedance, because ferrites are really good at creating inductors. And so we want to put a high impedance at the frequencies we're interested in so that we don't get any current flowing, common mode current flowing from one thing to the next. The differential currents can flow because they have no net magnetic field. And so you can see in this diagram down here that there's ferrites put in between each section here, but the author does this particular diagram actually kind of mess things up by tying them all back together again and calling that ground, that may or may not work out well. It depends. But that it kind of illustrates some of the ways that we can have a misconception about what to do in situations like this. And you can see that those ferrites, they create a low pass ARRL filter. It's a 3 dB per octave kind of thing. We can have more by wrapping more things around the ferrites, and so that gives us more series inductors. And lastly, stabilizing. This is really important too. If you have a lot of RF fields, because say your antenna system is asymmetric in some way, and you have a lot of current flowing around down the coax on the outside, that can cause high fields next to your rig inside your shack. And so we want to reduce those. And the way we reduce that is with counterpoises. And counterpoises are quarter wave segments of wire for each band of interest. They have to be kind of tuned. And you can have one for each band and then tie them together with a zip tie or something like that. And the idea here is to reduce the electric field and magnetic field gradients, but it's mostly the electric field ones that get you. And these will sort of change your antenna system. They could actually make it better. Who can say? Depends on how it goes together. But as this diagram here tries to say, and I put a question mark there, do you tie this to Earth? I'm not sure about that. I'm not sure that'll be a good thing. So with all of this, where did those ground rods go? Well, outside of lightning, I think you're mostly wasting your time. They can make things better, they can make things worse. It's hard to say. And I've heard both situations where people have come to me and said, oh yeah, I have a ground rod. As soon as I put that in, all the noise went away. Maybe that's the case. It's hard to say. And on portable antennas, I have a portable antenna that had a spike on the bottom. And the person who made the kit for that antenna connected the outside shield of a BNC connector to that spike into the ground. I just disconnected that and threw it away because I wanted the radials to be doing the job of sucking the RF out of the ground or trying to intercept it before it went in. I didn't need to be pumping any more RF in that direction. So for many years, I operated a second floor station in an apartment. I had a helically wound vertical dipole that was, I had to tune it like crazy to get it to work. But I worked the world with that thing, an AL811 amp, an IC7600, and not a ground in sight. And I did that by following the principles, shielding all the components, and some had their own shielding already embedded in them. Any additional shielding I put in. Ferrites everywhere, liberally sprinkling ferrites everywhere is a great plan. It fixes all kinds of problems. I had a problem with my stove when I swung the beam around in a particular direction and it would go crazy and crash the little computer inside. So I just put some toroids in there and I was good to go. And then stabilization of putting the counterpoise on all bands. You may not need that unless you have RF in the shack. It depends. So what about all these ground lugs in the back? What do you do with them? Well, I would say, kind of connect them together more than anything else. That makes sure that everything is at a relatively similar potential. And then connect that to the counterpoise bundle. I usually stick that on the amplifier just so that it's near where all the power is. And that's the idea here, is to kind of stabilize it within all of these RF fields and avoid RF burns. And that if you've ever had one of those, you really don't want one. And then, just kind of bond them together so that they're relatively the same. There'll be some differences because a wire is not really a wire like it is a DC when you talk about RF. And should you connect this to the ground rod? Not necessarily a good idea, and we'll talk about that. And here's a case where I had taken the rig out to a field day site, and I totally forgot to reconnect the ground. And guess what? Nothing bad happened because the shields were pulling everything in to be the same potential. It's just sort of one more layer of safety, but not an essential piece. This applies to HTs. HTs have a notion of, this side of the connector that some people think of as ground, but basically you hold it up and you have a quarter wave whip, for example, and then you hold in your hand and you're like the other half of the antenna. Antennas always have two halves, and you're not a very efficient other half of the antenna. It's a salty water bag. So if you add a piece of wire onto that, you can make the antenna work much better. I've seen several dB of improvement, but this brings up a point that I haven't touched on, which is that when you have these counterpoise wires, and one on your HT is just like a counterpoise, the ends can have very high voltages. And so even with 5 watts, you can feel that voltage tingle if you happen to touch your arm with it. So if you use those counterpoises on HF with an amplifier, they can have very high voltages. So fold them over and tape them so that you don't get into trouble with anything arcing. Now here's a case for ground, sort of. So we're going to go back to DC and talk about lightning. So what is lightning? It's a very complex subject. I'm going to oversimplify it to a large degree for this discussion. But you have clouds. They tend to have a negative region on the bottom, positive on the top. Those negative charges on the bottom pull positive charges up from the Earth's surface over a fairly wide range. And we want a safe discharge here, because if it's going to discharge, because it's a very high field, it's probably going to break the air down at some point. This is a very simplified model of a lightning strike. We have a plasma that forms from the intense electric fields that are there. The ions, which are the free electrons and free nuclei, become charge carriers. The charge equalizes, and we hope that this equalizes in a very nice way and not through your radio, because that would be a very bad idea. We definitely don't want that to happen. What about lightning rods? So lightning rods have sharp tips, you may have noticed. The idea is to bring the potential of the dirt up higher, closer to the base of the clouds. And where you have high curvature is where you have minimal mutual repulsion. And so you tend to get a lot of charge carriers there, which increases the field strength. And so the lightning is sort of attracted to that high curvature area. And so that's why we have these kind of sharp points. The lightning might strike there, and if it does, a huge amount of current is going to flow down a very thick wire and into the dirt, and that is your safe discharge, we hope. Antennas are a whole lot like this. They're up high, they bring that charge state up to the top, and they have lots of sharp edges, and they're fairly efficient conductors too. So if you're going to ground this antenna, so-called, or connect it to the dirt, it's for lightning and not RF. That's the important part. Now, here's this thing where we're talking about, you'll recall the diagram from earlier. You had the shield of the coax wrapped around a wire that went to this ground rod. So this is a good idea for lightning, but we don't want to do it in the house. And I've seen this many times where people will have their antenna goes into the back of the radio, and then they take that lug on the back of the radio and they connect that to a ground rod. Well, that's inviting the lightning right into your house. That's probably something you don't want to do, and it's going to kill your transceiver. You want this outside the house. You can use a polyphasor device. There's some semiconductor style ones that basically melt into shorts. There's other gas discharge ones. Pick the one that's best for the type of lightning you get or in the amount, and get that away from your house so that it can get into a conducting patch on the dirt as quickly and easily as possible. And if you have that coax in your house during a lightning storm, throw it outside if you can. Get it as far away as you can. So with all of this, what happened to ground? Well, kind of went poof. Except for the lightning case, I didn't find it anywhere in my exploration. And what I learned is that it's all relative. There's no precise reference to anything. There's no 0 point out there, maybe far away, too far for me to care about. The Earth is a lousy conductor. It's also a lousy dielectric. We don't even have a way to define that dielectric very well. So it changes. It's sort of capacitive looking, but not very good. So what do? We shield our equipment from all of these RF fields. We isolate the various components from each other so that we have balanced currents in the connections in between equipment. We stabilize things as best we can in an RF field. using counterpoises. And except for lightning, those ground rods for RF are not doing much of anything for us. And most importantly, have fun on the radio. This is a picture from the California QSO party some years ago. We had 6 transceivers. We were running 1,500 watts on almost all the stations, and not a ground in sight. And we all lived to tell the tale and had a lot of fun too. So I think we have just about 4 minutes. I might be able to take one question.
Good morning, good evening. Kim Briggs, VK7KB. Thank you for your talk. My question is, feed lines coming into the shack, should they be underground? This is after your lightning protection system. So that sector, which could be 20 metres long potentially, from the protection equipment to the shack, what's the best situation there?
Oh, that's a very interesting question. So I don't know. The thing to think about is what is the current path going to be when you have a very large current? So lightning can be up to 250,000 amps. And so that 250,000 amps, if it can be well conducted through the lightning protection equipment into the dirt, then it won't matter as much. If it's at the potential of the dirt, it's going to be a better conductor than the dirt itself. So laying it across the ground or putting it inside the ground may not make a whole lot of difference now that I'm thinking about it.